TFF to get you the buffer exchange and the reconcentration. If we can crack that, then we've got a truly continuous single-pass process. But of course, in doing it, you've got to be able to understand the way you control your process. You've got to be able to understand what is important when you are controlling that process. So these are some of the indicators or some of the parameters for which you have to exercise a degree of control. And the more you can control in a very known and a very predictable way, the more the regulator likes you. Because if you can prove to them that when you fall off, when you come off a sweet spot and you fall off the edge of a cliff, if you can show that you're doing something different from that and you've actually got control, then your life is an awful lot easier. So one of the things that we're doing is introducing PAT, process analytical technologies, into our approaches to manufacturing these various different products by having inline or online analytical tools available to be able to give you real-time feedback to give you control. And what does control look like? Well, the curves on the right-hand side show what happens if you change flow rate. This one doesn't fall off the edge of a cliff, does it? This one's nice and smooth and controllable. Process engineers love this because you can control it. You can make an adjustment that is predictable. And that makes manufacturing life an awful lot easier if you do that. So what we have there, the green line and the red line, are purely and simply two different formulations of LNPs, different degrees of pegylation. Yeah, it so happens in this particular example. And on the left-hand side is an example of what happens if you do it and see what the effect is on the size and size distribution. So the blue line is run at 20 mils a minute through this device that I've shown you. And if you run that, then that's giving you a particle size, Z average, of around about 110 with a PDI of about 0.15. Increase the flow to 200 mils a minute, and you come down in size, and that means that you get also a narrower size distribution. So this time we're now down at around about 55 nanometers in size and a 0.06 PDI. All well and good, I hear you say. That's fine. Does it work? Is it efficient? Well, yes. This is a process that runs between 2 and 5 bar. The two processes I showed you earlier run at something in the region of 30, 40, 60 bar, with an awful lot of wear, an awful lot of maintenance, consumables. We have none of those with this process. That's a robust process. That graph on the left-hand side, believe it or not, is an N of 3. If you come up close, you can actually see the 3. And by the way, yes, we've got very good encapsulation efficiency. Don't take my word for it, take Professor Yvonne Perry's word at Strathclyde University, 97, 98% encapsulation efficiency. So both of those are telling you you've got a very robust, very predictable, very economic process. Your yield is high. You're starting in a great place for all the downstream activities. And talking of starting, on the ATA stand in the corner of the room, you'll see one of these, the Pathfinder. When I say that you can start at the smallest scale with this, I mean 200 microliters fed into a 96 well plate. 200 microliters with only one waste well before it settles down. So one waste well, about 300 microliters, and every other well after that, 200 microliters, is good stuff, giving you the graph I've already shown you. And you can play with this, and you can change the flow rate, you can change the flow rate ratio as you go. And this is the baby of the family, the one that's here on display. There's actually a bigger family of 4. So the baby on the top left is the one I've talked about. The one at the bottom right is the most capable. It'll give you litres of quantity of product. It will do so with continuous dilution, and it will do so very quickly. And it will do so to GMP. So put that in the right environment, and this single box, this single instrument, will take you from your very first sample all the way through to clinical material, to phase 1. And if that isn't cost effective, I don't know what is. What do they look like? They get a bit more complicated as you grow up the scale. And if that's not enough for you, as I say, the AXF4 is basically the big brother of the whole thing. So we've got one of those in construction at the moment, but right now, I haven't got a photograph to show you, unfortunately, but it is for 1 billion doses COVID or pandemic readiness plant. So in summary, we've got this as a continuous single pass process that we're looking at here. We've done the first 2 boxes where we say LNP formation and LNP stabilization. We're working on the concentration and buffer exchange, and of course sterile filtration. Everybody knows how to do that, don't they? So, coming soon to a hospital near you is one single 40-foot container containing everything you need from DNA, RNA, LNP formation, fill finish, all based on fundamentally the tiny footprint that this is. That'll give you 50,000 doses an hour if you really push it. That's going to need an army of nurses to deliver it, but that gives you a decent, timely response. And of course you can change the RNA so that you can start by putting your influenza and then go to malaria and so on, all very simply, because this is all stainless steel, all clean in place, all very, very GMP friendly. The FDA has one of these. They kind of like it. They're just installing it in their brand new, I mean they've had it for a little while, but they're building a brand new continuous manufacturing plant for formulation, and it's going in there. Thank you very much, ladies and gentlemen.